I've made this video as a guide for solo artists or small teams in how to use LOPs and USD in Houdini. It can be a complicated topic, and a lot of the information out there tends to focus on the benefits for larger studios. For people like motion designers and independent artists, it can be hard to parse all of the tutorials and documentation to determine what tools are useful for us. My aim with this video isn't to tell you what your workflow should be. I'm essentially aiming to speedrun the learning process that I went through in using LOPs and USD for the last few years, so the process will mirror how my own workflow has evolved as I've learned more about the toolset. I'll start with the most basic setup with some geometry, lights, and a camera to get the scene rendering, and then we'll augment that scene, steadily increasing the complexity while explaining new concepts along the way. I'll cover the scene graph tree and how scenes can be organized and structured, as well as how to cache and optimize networks, how layers work, such as when and how they're created, and how they can be flattened, stacked, and referenced, different ways of loading geometry of various formats, adding effects to a shot, in this case a simple particle effect, AOVs and render passes, Multishot Workflow, render and automation with tops, and finally, rendering directly through Husk, the standalone Houdini USD renderer. With all of that said, let's get started. We'll put down a grid for the floor, then add a SOP create and put some geometry in it. I'll go with the box and put it on the floor, then jump back up to the stage. Now, if we set the display flag on the grid, we just see the grid. If we display the box, we see the grid and the box. So this means that as we connect nodes, we're adding objects as we go. Let's add a camera and look through it. Then I'll click the lock to position it, and then make it a square aspect ratio. And lastly, I'll add a transform node to give it some animation. By default, the transform node will affect the last object created, in this case, the camera. I'll add a 360-degree rotation on Y for a turntable effect. Now let's see how this looks rendered in Karma. It's a bit boring with the default headlight, so let's add a light. I'll make it a rectangle, and then transform it with the viewport handles. And I'll up the exposure to make it brighter. If you click the diffuse button above the viewport, then you can click on the geometry to make the light aim at that point, and control click and drag to adjust the distance of the light from the surface. It's still a bit dark, so let's add a dome light to brighten things up a bit. Next, we need some shaders, so I'll add a material library and dive inside. Create a Material X USD builder, name it Material X Red, and dive inside that. On the Material X standard surface node, we'll make the base color a light red. Jump back up, and let's make a blue material by copying the red material and naming it blue. Then dive inside and set its base color to blue. Back up at the stage, we can click the Autofill Materials button to add the materials to the scene. Then, with Assign Geometry turned on, we can click this arrow next to Geometry Path and click Objects in the Scene to assign the materials. This looks good, so let's render it. Add a Karma node, which actually creates two nodes. A Karma render settings to set the render settings, and a USD render op to render the images to disk. On the render settings node, we'll set the output path. I like to add a $hip name directory. Then there are settings for camera and resolution, and here we'll set the renderer to Karma XPU, and set the number of samples. I'm setting mine low for this demo to speed things up a bit. If you want GI, go into Rendering, Limits, and bump up the diffuse limit to about 3. That's about it. Select the render op, set it to render specific frame range, and hit render. And here's our sequence. This took about 11 minutes because by default, it's starting up and rendering each frame individually. If you turn on Render All Frames with a single process, it'll batch the frames together and render much faster as long as there isn't a large difference between frames. Now those 100 frames render in just 3.5 minutes, which is much better. And so that's our basic scene setup. For a lot of artists, this approach is more than enough to get you going. But let's dive a little deeper and look at scene organization. Let's open up the scene graph tree. In the Solaris desktop, it's also labeled as Geometry Spreadsheet because it serves a similar purpose. The left pane shows us all of the objects called primitives in our scene, and the right pane shows the properties of each primitive. We can ignore the right pane for now. If I select the grid node, we can see that there's now only the grid primitive in the tree. And as I step through nodes, we can see them being added one by one. It's a bit messy with everything being thrown into the root level, so let's tidy it up. Put down a primitive node at the top of the network. Here we can type paths to specify new primitives, creating a basic structure for our scene. I like to have everything under a global shot primitive, and all geometry grouped together under that. Now, set the kind primitive here. As a rule of thumb, if there's geometry anywhere under a primitive, set its kind to group. As you can see, that's changed the icons in the scene graph tree to this little blue tree. With that done, we can now go through our nodes and edit the primitive paths to fit the desired structure. I'll also rename the geometry to make it clearer. Next, the camera and lights. By default, they already come with a transform primitive to group them together, so we just need to tell it to put them under the shot primitive. For the materials, I like to put them closest to where they'll be used, in this case under geometry. We're getting a warning that the material library can't find the geometry anymore because we've changed their paths. We can reassign them by dragging the primitives from the scene graph tree into the geometry path parameter. Lastly, our camera path has also changed, so in the render settings we need to point it to the new one. Speaking of render settings, we'll keep the render primitive at the root level because that's where the renderer likes to look for it. And that's our scene organized, with everything nicely grouped and named. If I reopen the viewport, you'll see that I haven't changed anything about how the scene looks. I've just made it easier to find things. But what if we wanted to add more primitives? Like a fill light, for instance. I'll do that the same way as we added the key light. And you can see that it's been added to the default light location. We could just manually change the path again, but that's a bit tedious if you have lots of lights, or if you wanted to move all of your lights somewhere else in the tree. Instead, let's be a bit more procedural about this. To start with, I'll reset all of the lights back to their original paths. Now we can detach them from the network, and instead of inlining them, we'll graft them onto the tree with a graft branches node. Connect the lights to the second input, then set the primitive path to where we want to put them, in this case under shot. And for source prim path, just put a slash, meaning everything at the root level will get grafted under the shot primitive. Now we can add as many lights to the scene as we want, and they'll automatically go to where we want them in the scene graph tree. No more manually renaming paths. The same principle applies to geometry. If I add another SOP geometry to the network, I'll call it cone, dive inside, and put down a tube to make a cone. If you look at the tree, you can see that it's being added at the root level again. So once again, let's just set all of our paths back to default, detach the nodes, and graft them back into place. In this case, grafting onto /shot/geometry, and set the source prim path to slash again. We can't see the new cone because it's inside the box. Let's dive into SOPs and move it to the front. It would be useful to be able to look through the camera to do this, but it's not appearing in the list. We can fix that by jumping back up to the stage, detaching the camera and transform, and putting them before the graft. Then if we connect them to the top of the geometry branch and dive back into the SOP create, the camera will now appear in SOPs and we can look through it. If we go back up again and move the cone to the bottom of our geometry branch, then we can also see the other geometry in SOPs as well. Now we can edit the cone mesh so it's not hidden inside the box. Jumping back up, everything looks okay, but there's a slight problem. If you select the geometry graft and look at the scene graph tree, you'll see that we're now grafting a copy of the shot, geometry, and camera primitives as well. This is because connecting the camera to the input of the geometry branch added it to the tree of nodes being grafted. To stop this, we can insert a layer break at the top of the geometry branch. This essentially tells the network that all of the nodes above the break are for reference only. So we can still see them in the tree and in SOPs, but they aren't being included in operations like grafting. So with that done, we're back to where we were. Our scene is tidy and well structured, but now we don't have to manually edit paths all the time. The last thing to look at is optimization. With the display flag on the bottom of the network, I'll hit play. Such a simple scene, and I'm only getting about 12 frames a second. That's pretty terrible. The culprit is the camera animation. If we zoom in, you can see the little green time varying badge. This badge will flow downstream, making every subsequent node time varying, forcing every node to recook on every frame, which is very inefficient. To solve this, we can simply cache the animation, either with a cache node and setting it to cache all frames, or just by setting the transform node to sample frame range, which will do the same thing. Great, now we have real-time playback. But what if we have some heavy geometry that's animating? For demonstration purposes, I'll dive in and add some animated noise to the box. We've got those nasty time varying badges again. While the cache node will still work here, it's better to cache to disk instead. Put down a file cache. I'll name it cache geo, set it to evaluate for the full frame range, and hit save to disk. Now the animation is cached, so the badges are gone and our scene is nice and snappy again. That speed doesn't just apply to playback. It also means that our export times will be fast. Let's try. Put down a USD ROP. I'll name it export shot. We'll save it into a USD folder, set it to render the frame range, and hit save to disk. That export was basically instant. Let's bring it in to see what we saved. To load a scene in LOPs, you can use a sublayer node and point it to our exported USD file. And there we have our entire scene. The whole scene graph tree saved into a single file. It even has all of the render settings. So if we wanted, we could attach our render op to the sublayer and it would produce the same result when rendered. Okay, so we've gone over how to organize and cache scenes. The sublayer node is hinting at where we need to look next. Let's dive into the world of USD layers. So we've saved our scene as a USD file and loaded it back in as a sublayer. But what exactly is a layer? Let's take a look at the Scene Graph Layers tab. This shows us all of the layers that make up our current scene. And here, under root, is our exported USD file. So layers are essentially just USD files. The root layer is kind of the same. It's essentially just a USD file that hasn't been saved to disk yet. If we select our render settings node, we can see 3 layers. But when we load the USD file, we only see 1. Under save control, you can see that these layers say implicit. If we look at the USD ROP, under save style, the default is flatten implicit layers. So we ended up with 1 layer because the USD ROP flattened our layers together for us. Before we get into what we can do with layers and how to manipulate them, let's first look into how to know when we're creating new layers. In the network view, you should be able to see your nodes lit up with different colors, with each color representing a layer. Nodes with the same color are all contributing to the same layer. If you don't see the colors, go to View and turn on Show LOP Layer Colors. If I step through the nodes, you can see that many of the operations are simply adding to an existing layer, while some, like render settings and SOP create nodes, are creating new layers. That all makes sense, but why do we end up with only 3 layers when there are so many more colors? Let's take a look at the lights. If I detach them from the graph, you can see they're still their own layer, and they all share a color. So layers can exist separately from our main network and not contribute to the output. Alright, but this one is connected, and the lights are clearly ending up in the output. So where did the layer go? In the Layers panel, if I select the light layer and open up the right panel, you can see what exactly is going into the layer. Don't worry too much about what all this says, we'll just focus on what's relevant to us. Selecting the first light, you can see that we're defining an XForm named lights. And under that, we define a light named light1. Scrolling down, you can see all of the properties of the light. If I select the next light, you can see it being added to the layer. There's now a new light being defined under lights called Dome Light 1. Similarly, I can scroll down to see all of the light properties. Now selecting the last light, you see that being added as well. If I switch back over to the scene graph tree, you can see this matches exactly what's been defined in the layer. Great. Now let's step down the other branch. To make things clearer, I'll disable the geometry graph in the camera for now. I'll select the primitive node and look at the scene graph tree. From what we saw before, we should expect that this layer will contain definitions for 2 XForm primitives named shot and under that geometry. Opening up the layer panel and looking at the code, that's exactly what we see. We define an XForm named shot, and under that an XForm named geometry. Now if I select the graph, you can see that our lights appear as though they were inlined under the primitive node. The only difference being that instead of the lights XForm being defined at the root level, it's under our shot primitive where we told it to go. This is a handy feature of graph nodes. They allow you to copy specific primitives from the right input into specific places in the layer on the left input. This is really useful if you want to pull in some or all of the data from a layer, like a file on disk, but don't want your output to keep pointing to that file. But what if we do want to keep referencing that right-hand layer? We use a reference. Like sublayering, referencing can pull in USD files, but instead of pulling in the whole file as it is, we pull in specific primitives and put them into specific locations. So you can think of it as being similar to the graph branches node, but the graph is operating on layers in memory, and the reference is pointing to layers on or bound for disk. If our lights were already on disk as a USD file, we could load them using this file pattern parameter. But since they only exist in the network, we'll use the multi-input options by connecting them to the right input. Now that we've hooked up the reference node, let's see what it's doing. By default, it'll reference a primitive from the root level of the right input into the root level of the scene, and its name will be the name of the last node on the right input. In the scene graph tree, that's what we see. The light XForm is at the root of the scene, and it's named light2 after the last node on the right. The XForm is now also green. This means that the primitive has a composition arc. A reference is a type of composition arc, so in our case, green means it's being referenced. To get this XForm back to where we want it, I'll set the primitive path to /shot/lights. Perfect. If I toggle between the graph and the reference, we now get the same result. The only difference being the reference version is green. Switching over to the layers panel, and we now have a new layer under the active layer with this little post-it icon telling us it's a reference. If I select the active layer and inspect the code, we no longer see the lights in there. The lights stay defined in their own layer, so instead we're just defining a primitive that references that layer. So now when we export our USD scene, we'll export two files. A USD file with just the lights, and the main scene that references the lights USD. We have a warning on the reference. Let's see what that's about. It says here that a multi-input connection has no save path set, and so one will be generated. Let's see what that means. I'll connect the reference to the material library, and on the USD ROP, hit save to disk. The ROP has a warning for us, telling us where the light layer was saved, because we didn't specify a path. In the File Explorer, we can see that Houdini has indeed made a folder called Stage, and saved our lights in there. Let's delete this stage folder, and set a proper save path so that Houdini will stop complaining. I'll rearrange the nodes a bit, and append a configure layer after the lights. Check the checkbox, and set a path. I'll just say hit USD lights USD. In the Layers panel, you can see that the layer is now explicit and has a save path, and the warning on the reference node is gone. Let's save to disk again. No more warnings, and the lights got saved where we told them to. If I sublayer the scene back in, you can see that we've preserved the reference to the lights layer on disk. You can do this with any part of your scene that you think you might want to reuse later somewhere else. Sticking with the theme of lights, if you do this enough, you could build up a library of light rigs to reuse on new projects. Personally, I don't often save out things like lights, but for geometry caches, it's essential. Let's apply our newfound knowledge of referencing to the geometry. If you look closely, we're already halfway there. Unlike the lights layer that doesn't exist on disk until we export the scene, we've already cached the geometry to a single layer on disk. If you dive inside the file cache, you'll see that it's just a wrapper around a USD ROP and a sublayer. So if the geometry is already saved to disk, then grafting it back into the scene and saving it again means we're duplicating the data. This is pretty wasteful and would be really slow for heavy caches. So let's reference it instead. Because the cache is already on disk, we could point it to the USD file in the file pattern parameter, but then if we update the cache version or change the save location, we need to remember to also update it here. So instead we'll use the multi-input again. In the scene graph tree as before, we have a green reference primitive named after the last node on the right input. The little C icon and the kind show us that this is a component primitive. This is what assets are usually saved as, and what the SOP creates will make by default. But why is there only one, the cone? If I select the cache, you can see it clearly has three components. I mentioned before that a reference can take a specific primitive and reference it to a specific location, but you can't reference the root level. We can choose the primitive we want to reference by setting the reference primitive parameter to reference specific primitive, and setting the path. /box for instance. If I want to reference everything, I'll need to connect the cache 3 times. Then in the inputs box here, I can specify the paths and the primitives to reference. So I'll reference /box onto /shot/geometry/box, /cone onto shot geometry cone, and /grid onto shot geometry grid. If you look at the scene graph tree, as I toggle between the reference and the graft, you can see that the geometry is back where it belongs and it's now being referenced. This is a bit clunky though. We had to manually set all the paths again, and having all of the geometry in one file at the root isn't ideal. It's fine if you're saving a library of assets or something, but in this case, if we want to change any of the geo, we'd have to save the whole cache again. So here's a cleaner approach. Delete the reference in the file cache, then detach the SOP create nodes and lay them out horizontally. Now merge them together and connect that to the graft. The merge will take the 3 geometry layers and flatten them into one layer. We're back to where we started, but now we can selectively cache the objects in our scene. We only really need to cache the box, so let's do that with a new file cache. I'll name it cache box and hit save to disk. With that saved, we want to reference it. So we'll put down a reference between the file cache and the merge, with the file cache connected to the multi-input of the reference. If you look at the scene graph tree again, you'll see that the box has been renamed to cache_box, and it's now being referenced. Let's name it back to box here. This setup is nice and clear. You have all of your geometry laid out. It's easy to see what's being referenced versus saved with the scene, and it's trivial to extend. Say the cone model became really heavy, and you need to cache it. Simply put down a file cache and connect it to the reference instead of the merge. Now we're still grafting, which discarded the connection to the cache on disk before, so why are the references being preserved? Well, as we've covered, the graft copies primitives from the layer on the right, so let's select our merge and look at the active layer to see what the graft is copying. You can see that we have one implicit layer that's referencing 2 layers from disk. Inspecting the code, we see the grid being defined, and if we scroll past that, we see the box and the cone being referenced. This is what's being grafted and why the graft is keeping the references intact. The graft isn't copying the contents of the reference files, it's copying the code for the reference itself. And we can confirm that by selecting the graft, inspecting the layer, and there's our grid followed by our references. Let's go back to our USD ROP and save to disk. This will save the lights USD and flatten our other layers into the export USD. And if I sublayer that back in, you can see our scene exactly as it was before, but now instead of being a single layer on disk, it's composed of 4 separate files. But why does this matter? Because not only can you store and reuse parts of your scene as assets, your scene exports are now much more lightweight. It doesn't look like much here where we've gone from 45 kilobytes down to 25, so let's look at a real production example. Here's the USD export from a project I worked on in 2024. This is the file I used to render a 30-second shot at 24K by 2K resolution, loading about a terabyte's worth of fluid sim and whitewater caches. And that whole scene saved down to 115 kilobytes almost instantly, because it's simply referencing files that already exist on disk. But what are these manifest and topology files? I'll touch on that next when we go over the various ways of loading geometry into our scenes. But before we move on, there's one more very important thing to cover while we're on the topic of layers, and that's layering. Layering is an important concept to understand in LOPs. USD calls this concept composition arcs. We've already covered using a sublayer to bring in primitives to your scene, but what we haven't covered is how layers can stack and override each other. Here, I'm sublayering a simple box. Then I can sublayer some animation. I can sublayer a completely different mesh, like this crab from 3D scans, and I can sublayer a material with its assignment. So each new layer can add to or override information from the previous layers. The USD term for these overrides is opinions. Another composition arc we've covered is referencing. Here you can see we can achieve the same result of overriding primitives using references. However, it's important to understand how these different composition arcs mix. If I try to reference the animation, crab, and material onto the box sublayer, only the material seems to work. Why is that? Composition arcs have a strength ordering that decides which opinions take priority. Locals, inherits, variant sets, references, payloads, and specializers. This ordering is referred to as LOPs. The E for relocate seems to be a new one, so I don't think there's a node for it yet in 20.5. I won't go into all of these here because the video is already going to be quite long, but you can see that local and sublayer arcs are higher in the list than references, and are therefore stronger. This is why we couldn't use the references to override the box, because the sublayer with the box already has opinions on the transform and the mesh. And those opinions are stronger than the referenced opinion on the transform and the referenced opinion on the mesh. The material and material binding still worked, because the box layer didn't have any opinions on those. Now let's take a look at loading geometry. There are many different ways of doing this in LOPs, and here are just some of the nodes that you can use. On the left are nodes for importing geometry created within Houdini. The scene import and the SOP import nodes will pull in geo from the object and SOP contexts, respectively. The SOP create, as we've already seen, is a convenient wrapper around a SOP network and a SOP import that allows you to dive inside to create geometry. In the middle here are nodes for pulling in USD files. They can also load Alembic files, which is useful for pulling in cameras supplied by clients that aren't using USD yet, and they can even load BGO files, but I prefer to load those inside of a SOP create with a file SOP. We've covered sublayers and references, but as a quick recap, sublayers are for loading in anything from scenes to meshes to overrides, and they'll load the file as is, while references are mainly used for loading assets into your scene. They'll load specific primitives and let you put them wherever you want in the scene graph tree. The asset reference node is a wrapper around the reference node that gives you a transform handle and lets you set variants. These three nodes also have time offset options for offsetting and scaling the timing of files as you bring them in. It's useful for altering the start frame of animations to match your shots. Load layer is like a sublayer, but it loads into memory. It's useful for when you need to make destructive edits to a file. These three nodes on the right are for special cases. The volume node is for pulling in VDBs. Under the volume primitive, you can see the fields loaded in. If you're loading a VDB sequence, you want to cache it or set it to sample frame range to remove the time dependency. Geometry sequence is another wrapper around a SOPnet and a SOP import that's designed to load BGO sequences. It's useful for loading sequences to edit in LOPs before caching to USD. I don't really use this as I prefer to just use a SOP create. The last node, geometry clip sequence, is great for really heavy caches. For those, saving to a single USD file can be unfeasible, either due to memory limitations or file size issues. So you save them as per frame USD or BGO sequences instead. The geometry clip sequence loads these per frame caches as USD value clips. This is the one case where I will occasionally use BGO files at the LOP level, particularly for things like fluid sims, as it allows you to reference BGO files on disk without needing to recache them to USD. There are some quirks to keep in mind though, so let's walk through how to set it up. Uncheck Get Geometry from second input, and point the load clip file path to your sequence. I'll load the same flower BGO sequence as you saw on the geometry sequence node. BGO sequences need a sample frame to tell USD what time samples to use for each frame in the sequence. You can add it in SOPs with a USD configure SOP, but I tend to just add it here by appending this SDF format args string to the end of the file path. Now set the clip primitive path to the primitive you want to load. BGO sequences likely won't have paths set, So in this case, you just set it to /geometry. You can now see the sequence, but it's quite sluggish. There are a couple of settings to fix that. This node works by creating a couple of extra files called topology and manifest that store a snapshot of the scene graph hierarchy of the file sequence. By default, Houdini is assuming that the hierarchy and attribute list are changing throughout the sequence, so it needs to process every frame to produce these files. If the sequence has a consistent hierarchy, then check all clip files have matching scene graph structure. Now the manifest and topology is sourced from a single frame, which is significantly faster. Next, I can uncheck flatten clip files, as we're not loading USD files, so there's no composition arcs to flatten. Now I just have to set the start frame and cache the sequence to get rid of the time dependency. In this case, I'll just set it to sample frame range. And with all of that done, you should now have a USD scene pointing to your heavy file sequence. Let's go back to our earlier setup and look at adding effects for a shot. But first, let's reorganize the network a little. We'll call this render. We'll call this structure, reference geometry, graph geometry, material library geometry, reference lights, and configure layer lights. I don't like these wires being twisted, so I'll swap these around. Cool. Now let's disable the turntable animation and the box animation. And I'll just recache the box since we've already set it up that way. Let's move our material library before the graft. That way it's visually grouped with the geometry it applies to. And we'll reset the path here to be at the root level so that it gets grafted into the correct position along with the geometry. The materials are created under a scope primitive, indicated by this circle icon. A scope is a primitive that's used purely for organization, as it can't be transformed. For the sake of organization, we'll put the geometry under its own scope as well. After the merge, put down a restructure scene graph. Uncheck flatten input layers, and set new parent prim to /geo. So now we have a geoscope with all of our geometry in it. And I'll need to update the material assignment now that we've changed the paths as well. Lastly, I'll change the frame rate too. We'll start at 1001, that way you have room to append frames to the front if you need pre-roll, handles, or if the edit changes. Done. Now we can add a bit of effects into the scene. This is done in the same way as the geometry. After the geometry graft, add a layer break and a salt create. I'll call it particles. Then dive inside. Here I'm pasting a simple particle setup. Say we want to have particles interact with the geometry. We can pull in the geometry with a LOP import. Under LOP path, we could put the path to a node from the LOP network, but since we have a layer break connected to the SOP create, we can use the expression op input path. We need to reference 3 levels up because of how this SOP network is nested, and the input number is 0. Click the arrow next to primitives, and we get a handy tree of primitives we can choose from. I'll go with box and cone. Then set it to static as the geometry isn't animating. That brings in the geo as packed USD primitives, which you'll need to unpack with unpack USD to polygons. Now, if I want to only emit from the cone, I'll need to blast the box. It's cutting off screen, but in the dropdown, you can blast by the path attribute. I'll select the cone and check delete non-selected. If we connect that to the source and connect the unpack to the collision, we see particles emitting and colliding. Now, before we leave, let's clean up the attributes as we don't necessarily want to cache them all. I'll put down an attribute delete, then set it to delete non-selected, and I'll keep the velocity, ID, and p-scale. Jumping back up, let's cache the particles using a file cache, same as we did before. Then, same as with the geometry, we'll reference the backend, setting the name to particles. Add a geoscope with a restructure scene graph set to parent under /geo. Then I'll make a bit of room to add a material library, which I'll graft onto the main scene tree. In this case, onto shot effects. And I'll set the kind to group and the source prim to the root level. So now we have an effects group under the shot primitive. You could also have defined the effects group up here if you knew the shot was going to have effects ahead of time. We still need a material for the particles, so we'll jump inside the material library. This time, instead of a USD material X builder, I'll add a Karma material builder. I'll explain why when we cover passes next. Dive in. I like additive glowy particles, so let's put down a material X surface unlit, set its transmission to 1, and connect it to the material output. We can delete the other shader and displacement node. Then I'll jump back up, hit autofill materials, and assign the shader to the particles. Let's display the render settings and switch over to Karma XPU so we can see how it renders. It's looking good, but there's no motion blur on the particles. So in the render settings, go to Rendering, Camera FX, and set the velocity blur parameter to velocity blur. Great. Lastly, I'll add some network boxes to group the nodes together nicely. One for geometry, one for effects, and one for lights. Now we can move on to talking about AOVs and passes. To add AOVs to your render, in the render settings, go to Image Output AOVs. Here you can add all of the usual AOVs. That's all fairly straightforward, But how do you create mats? Let's start with Cryptomats. Under Extra Render Vars, click the plus button to add a new AOV. Click the arrow next to name, and unfortunately it's cutting off the screen, but right at the bottom are a couple of options for Cryptomat Object and Cryptomat Material. I'll add a Cryptomat Object. If I turn on Karma in the viewport and click the Render Outputs button, we can see the new AOV in the list. You'll notice that the particles aren't appearing in the Cryptomat. That's due to a quirk of the unlit shader when it's set to transmissive. For now, I'll turn that off, but we'll revisit it later. Sometimes Cryptomats are a bit overkill though, and you just need an RGB mat. Click the plus button again to add a new AOV and call it mat. Format controls the number and precision of channels in the AOV when saved. I'll set it to color 3H, which is 16-bit RGB. Now set the source type to primvar, which is essentially a LOP level attribute. The source name is the name of the primvar to look for, so I'll just call it mat. Data type is the type of the primvar values, and I'll leave this as color 3F. I'll zoom into the bottom of the network and add the mat primvar with a material variation node. Then I'll drag the box into the primitive parameter, name it mat, and set its type to color 3F to match the AOV, and I'll set its color to red. If we take a look at the mat in the render outputs, we now see the red cube mat. Let's copy that material variation a couple of times to make the cone green and the particles blue. And I like to name the material variation nodes red, green, and blue, and then color them like this to make it clear what they're doing. Now that's the object-based mat done. What if we wanted to generate a mat from material properties? Click the plus again to add another AOV, and I'll call it material mat. Again, set its format to color 3H, name it material mat, and leave its source type as raw. If I switch over to the material mat in the render outputs, it's currently black, so let's fix that by diving into the particle material. The reason we made this a Karma material builder is so we can add a Karma AOV node, which lets us put shader data into AOVs. Name the node material mat to match the AOV, and uncheck create render var, as we've already created the render var ourselves. Now connect it to the next input on the material output node. Next we need to plug in some data, so let's pull in some with the geometry property value node. This lets us read primvars or attributes from geometry. I'll open up the scene graph tree and check the data in the right pane to see what primvars we have on the particles. We saved ID, vel, and p-scale, which got remapped to IDs, velocities, and widths. Let's pull in IDs. It's an integer, and there are about 3,500 values. I can close this now, and then on the geometry property value node, I'll set geomprop to IDs and the signature to integer. If I plug this directly into the AOV, nothing will happen, as we're plugging an integer into a color. So let's add a Karma ramp constant in between and set it to infrared to help visualize. The ramp is expecting values in the 0 to 1 range, and the IDs are in the 0 to 3,540 range. So we can remap the values with a material X range node, plugging the property into the import, and setting in high to 3,540. That's cool. We have a gradient running from the first particles emitted to the last. We could call this AOV done, but we have 3 channels that we can fill. So what else can we do? Add a material X random float and connect that to the ramp. Now we have a random value per particle, which could be useful in compositing. For the last channel, let's do particle speed. Add a new geometry property value, set it to vector 3, and pull in velocities. To calculate the speed from the velocity vector, we need its magnitude. So append a material X magnitude node and connect it to the ramp. Now we have a path with the hotter colors denoting faster particles. We can remap this with a range if there's too much red. So now that we have 3 data channels, we can combine them into one AOV with a combined 3 node by connecting the 3 input channels and then connecting the output to the AOV. And now we can delete the ramp. We could totally have made these 3 separate float AOVs instead of a single color AOV, but this way we get to cover how to combine and manipulate multiple channels. Going back to the color output, we can see that the particles look a bit dull and are casting shadows. What if we want them to just be little glowy balls of light? On the surface unlit node, I'll set the transmission back to 1 to make them additive again. But now they've disappeared from the mats. So if we want to separate the particles, we'll need to put them in a separate render pass. The workflow I'm about to show you will likely change in Houdini 21 with the addition of render pass primitives, but for now this is how it's done. I'll detach the render op and move it out of the way. We'll need 2 branches after the render settings. We could duplicate the render settings node, but if we want the passes to share mostly the same render settings, that can get annoying, as if you need to update the render settings on one, you'll likely then need to update them on the other. Before we move on, let's take a quick look at how the render settings are stored in the tree. Under this render scope, there is a render settings prim. As its name suggests, this stores all of the render settings. Scrolling through the right pane, you can see all of the Karma settings. At the top is the render camera and the render products. They're red because they're pointing to other primitives. Under the product scope, you'll find the render product. This is the image we want to output. Scrolling through the right pane again, you'll see image settings, color space options, resolution, and product name. This is the save path for the renders. Scrolling back up, there are two more red properties, the camera again, and ordered vars. Expanding that shows us the list of AOVs that will be included in the rendered image. Back in the tree, under the vars scope, you can see all of the available AOVs. Now, going back to the problem at hand, if we want to save out two separate passes, then the first thing we need to do is set two different output paths. We now know that's controlled by the product name on the render product. So to change that, we can put down a render product edit, and I'll call it geometry, which will be the name of the pass. We need to point it to the render product primitive. The default expression will work if this node comes after a render settings lot, but I'll set it explicitly by dragging the render product into the primitives parameter. Click the circle next to product name and select set or create to set the render path. Here's how I like to set my paths. hip/render/hipname/os/hipname.os.f4.exr. So you render into a folder per pass, per Houdini scene file, inside of the render folder. Since we're putting the particles into their own pass, we'll remove them with a prune node by dragging in the effects primitive and setting the method to deactivate. For the particles pass, we can copy the render product edit and prune to make a new branch. I'll name the pass by renaming the render product edit to effects, and since the matte AOVs don't work on the particles, we don't need them in this pass. So under ordered render vars, we'll just set it to beauty. Now on the prune, we could deactivate the geometry, and we'd be left with the particles. But then we'd lose the glows and reflections they cast on the geometry. So instead we'll prune the lights. Now that there are no lights in the scene, it's creating the default headlight, but there seems to be no way to turn it off, which I think is probably a bug. There's a setting here called automatic headlight creation, but it doesn't seem to work. So a temporary workaround is to just add a light and set its intensity to 0. The render's looking a bit noisy, so I'll increase the samples with a render settings edit, pointing it to the render settings prim, and bumping up the path trace samples. That's certainly looking better, and while this pass is working fine, it would probably be a bit more useful if we separate the particles from the lighting contributions. We can do this by making the geometry a holdout. Add a render geometry settings lot, and set the path to shot geometry. Then scroll down to shading, and set the holdout mode to matte. Now the geometry has disappeared. If we hover over the holdout mode parameter, the tooltip tells us that this will redirect any lighting contributions to the holdout AOV. So let's add a holdout AOV. We could add it on the render settings node, but since we only need the AOV on this branch, I'll add it with an additional render vars node. In the dropdown next to name, select holdout. It won't show up in the render outputs yet, because we need to add it to the ordered render vars list on the render product. Now we have their particles and their lighting contributions in separate AOVs. It might be hard to see, but the holdout is looking pretty noisy. We could keep bumping up the samples forever, but that noise will never go away, because by default, Karma will only refine noise in the beauty, not the other AOVs. To fix this, on the render settings node, under advanced and sampling, you need to change the pixel oracle from variance to uniform. We only want to do this on the effects pass though, so we'll change it back and set it on the render settings edit instead. Under image, change pixel oracle to uniform. And that's our two render passes all set up. There are a few ways to render them now. We could connect the render lot to the first branch and then hit render, and then connect it to the second branch and hit render again, but that's a bit tedious, especially if you have more than two passes. We could duplicate it so we have one render op for each branch, and that way we can select them both and hit render to render them one after the other. But while this works perfectly fine for most cases, it does mean that if we change settings on one render op, we'll need to remember to change them on the others. The alternative is to use context variables and tops, but we'll cover that after we go over how to expand this setup for a multi-shot workflow. Now, before we get to how to set up multiple shots, there are a couple of key concepts that make the whole thing work smoothly. The first is camera switching. Here, I'm referencing a pig head and defining a camera. Then I use a camera edit to position the camera for each shot. If I look through the camera, you can see that as I switch between branches, the viewport is automatically switching. This is because the camera on each branch has the same name. But this won't always be possible. In this example, I have the same pig head and the same shots, but the cameras are named per shot. Now, when I switch shots, the viewport switches to no camera, and I need to manually tell it to look through the camera again. To fix this, for each shot, you just set your camera in the render settings. So in this case, camera 1 and camera 2. Now, instead of selecting a specific camera, you select render settings camera, and the viewport will automatically switch between cameras again. And just as it's likely that you'll have multiple cameras between shots, It's also likely that you'll need to render different frame ranges. Manually changing the global animation options would be incredibly time consuming. So thankfully, there's a very helpful button here named Stage Frame Range Drives Playbar Range. Let's turn it on and see it in action. If I put down a configure layer above the pig, I can define the global frame range. I'll also set the frame rate. I'll get to why in a moment. You can see that the playback range automatically updated to match. If I want to change that frame range per shot, I can add another configure layer for each branch and set a shot-specific frame range. Now, displaying each branch will adjust the frame range accordingly. But something to be very mindful of when using this feature is that it'll also adjust your scene's frame rate. To demonstrate, I'll add a SOP create on the first shot and set the frame rate on the second shot to 30 frames per second. You can see that as I switch branches, the playback range and frame rate both change. If I have my display flag on shot 2 and dive into the SOP create on shot 1, I'll end up in SOPs with the wrong frame range and frame rate. This is particularly dangerous when pulling in assets with frame rates authored. It bit me particularly badly once when working with a bunch of Alembic cameras. A few of them had been incorrectly authored at the wrong frame rate, so they would change my scene frame rate when displayed, and it threw off a lot of my animation. Learn from my mistakes. When using the Stage Frame Range button, I recommend always starting your network by explicitly authoring the frame rate, and get into the habit of displaying your SOP creates before you dive in, to ensure the animation options are set correctly. Going back to our single shot setup, let's put that into practice by putting a configure layer at the top of the network and setting the frame rate and frame range. Then turn on the Stage Frame Range button, and now we can get to handling multiple shots. Like with everything in Houdini, there are many different ways of handling multi-shot workflows. The simplest of which is to simply have separate vertical networks for each shot. This is totally fine and will get the job done, but if there are a lot of shared elements between shots, there's a better way. It's all driven by the switch LOP. We'll put ours after the render settings, call it switch shot, and then make some room. We're going to make a separate branch for each shot. To start with, I like to define the shot range with a configure layer. I'll name it after the shot, so configure 1. Now I can use a camera edit to position the camera and adjust its properties. For the next shot, copy the nodes across, then set the frame range again, and edit the camera. This time I'll go for a low angle with a wide lens. I'll copy the nodes one more time to make a third shot, and this time I'll animate it to have the camera do a quick dolly backwards that eases to a stop. It should go without saying that you can do anything you like on these shot branches. You can of course edit primitives, but you could also prune to remove primitives. You can animate primitives, and you can create reference or sublayer in more primitives. I'll plug all of these shot branches into the switch, and we can now switch between shots. Now we'll need to update the render product so that each shot renders to a separate location. But if we take our approach from the last section and use a render product edit on each branch, then the pass product names will override the shot names. So instead, we'll drive the product name and the shot switcher using context variables. Open a panel and click the plus to add a new tab. Under New Pane tab type, Solaris, click Context Options Editor. Here we can define global variables for the scene. To add one, click the plus and select String menu. Then click the pencil to configure the variable. I'll call it shot, and we need 3 values, one for each shot. Then I'll turn on Automatically Generate Values, as I don't need name value pairs. Then click the pencil again to close. Now we can set the shot variable with this drop-down menu. But how do we use it? Let's start with the switch. Change the Choose Input parameter to by name, and in Select Input, we can put @shot in backticks. If I middle click the parameter, it shows that it's evaluating to the currently selected shot. The name the switch will look for in each branch defaults to the last node on that branch. So you can set the branch name with nulls, but in this case that won't work, as our shots are numbers and you can't name nodes that way. The alternative is to simply tell the switch node which name to use for each branch. So in our case, 010, 020, and 030. And now if I change the shot, the network will switch to using that branch. With that working, let's add another variable for the passes. We'll call it pass, and name the passes same as before, geometry and effects. We'll implement this in the same way as the shots. Add a switch just before the render up, I'll call it switch pass, and connect the branches. Set the switch to by name, and set the input to @pass in backticks. Switching the pass updates the input, and if we display it, you'll see that it works immediately, because the last node on each branch is already named the same as the pass. Now we can delete the extra render op, and I'll rename this one back to render. The last thing to fix is the product name. We want to set them all in one place, so I'll just do it on the render settings node. I'll add folders for shot and pass, and I'll also add the shot and pass to the file name. Middle clicking the parameter shows us that we're indeed getting a folder for the shot and the pass, and if we switch the shot in the context options panel, it'll update the product name automatically. And with that done, we can now disable the product name edits on the pass branches because we don't need them anymore. So now we have our single render op and our context switching ready to go. Now on the render op, we need to set the frame range to render frame range from stage. That way, when we hit render, the frame range will be set automatically per shot. The last thing to do is automate rendering these shots and passes. For that, we'll dive into tops. To automate rendering the shots and passes, we'll put down a top network and dive inside. We need to make work items for each shot and pass. So I'll put down a wedge, name it wedge shot, and set the count to 3 because we have 3 shots. Click the plus to make a new attribute. I'll call it tops shot, then set its type to string, and click the plus 3 times to add 3 values. These need to be the same shot names we used in our context options. Cook the node to see 3 dots representing a work item for each shot. If I middle click on one, you can see the tops shot attribute value. Make another wedge for the passes. Set its count to 2, call it tops pass, make it a string, and add the pass names. If I cook again, we now have 6 work items, 2 passes for each shot. To drive our network with these attributes, we'll need to override the context options. So I'll jump back to the stage, and just before the render op, put down an edit context options LOP. Here we can override the context options for every node above this one in the network. I'll replace shot with @tops_shot in backticks, and then click plus to add another override, and replace pass with @tops_pass, also in backticks. Now, with the display flag on the edit context options, I can click on the top net work items to see the shots and passes switching. And I can still put the display flag back on the switch if I want to manually change shots with the context options while working. With all of the work items set up, I'll jump back into the top net and add a ROP vet to drive the render op. Set its path to the render op, and under frames and batching, change it to evaluate using ROP node configuration. If we cook now, it'll try to render all the shots and passes simultaneously, which your computer will not be a fan of. So select the local scheduler and set the total slots to custom and 1. Now when I cook the network, it'll only render one work item at a time, so my computer won't explode. While it's rendering, you can double click on a work item to check the progress. If you want to be more selective about what gets rendered, you can use a filter by expression to remove work items. Say I don't need the effects pass for shot 1. I can use the string compare expression to compare the current shot to 010, then add an extra expression set to and use another string compare to compare the current pass to effects. Cooking the filter node now shows only 5 work items as we've removed the effects pass from shot 1, which we can confirm by right-clicking the node and opening the task graph table. If I sort by the top shot attribute, you can see that indeed the shot 1 effects pass is gone. And with that, we're basically done. We've covered everything that most solo artists would ever need to know in order to build and render their shots in LOPs. That said, there is one more optional level of complexity we can go to, and that's rendering USD files directly. If you take a look at the USD render op, under Output, you'll see options for USD export. This node is saving your scene to a temporary USD file and then passing it to the Husk command. If we save the USD file instead, then we can pass it to Husk ourselves. Then we can render without needing an instance of Houdini running. So let's swap this USD render op for a USD ROP. I'll call it export, and then set the frame range to render frame range from stage. The default export settings will be fine, we just need to set the output path. Since the edit context options don't affect this node, I'll need to use the tops variables for the shot and pass in the file name, and I'll save them in the USD folder under hip name. Going back into the top net, we can now point the ROP fetch to the USD ROP instead. But before we cook, I'll reset the local scheduler back to the default so we can export all the shots at once. Done. That'll spit out a folder full of USD files. So now to render them, we need to pass them to Husk, Houdini's USD renderer. I'll show you the manual way first, and then go over how I currently do it. You'll need to make sure that the Houdini bin directory is in your path environment variable. I won't cover how to do that here, but there's a million guides out there already. If you've done that, open your terminal. You can check that the path is set correctly by typing Husk and hitting enter, which should display the help docs. So to render a USD file, you use the Husk command, and then pass the USD file as an argument. Then you can add other arguments to control the renderer. Here are the main ones you'll need. Frame, to set the start frame. Frame count, to tell it how many frames to render. Engine, to select between CPU and XPU. Make output path, to tell it to create any directories that don't exist. And finally, verbose A, which will give you progress updates during the render. If I hit enter, the render will immediately kick off, and we can see the files appearing here. If you're only rendering a couple of shots, this might seem like overkill, but it does save a lot of time opening Houdini and switching scenes, and it saves the computing resources from having Houdini open. You can check out the Houdini docs for more info. They cover all of the arguments you can give to Husk. And while we're here in the terminal, there are a few other cool USD tools that ship with Houdini. There's USD Cat, which will print the contents of a USD file, and you can also use it to convert between binary and ASCII formats with the -O flag. Here I'm converting the binary file to an ASCII one that you can open up in whatever text editor you like. There's also USD View, which will let you open and inspect the contents of any USD files. The downside of the version that ships with Houdini is that it has to run through Houdini's Python interpreter, which is a bit finicky to get working, and it's quite slow to start up. But the upside is you get a bunch of Houdini-specific features like karma rendering, and I think also BGO support and procedurals. In practice, I have USD files mapped to the precompiled USD download that you can get from NVIDIA, so I can just double-click USD files to open them in USD View really quickly, but without the karma support. And that's it for terminal land. I should stress that most artists won't need to use the terminal or those tools. I just think they're really useful, and it's good to know that they're there. Now for how I render USD files. I use Deadline, specifically with a custom Husk standalone plugin that you can find here on GitHub. There is an official submitter, and it might be better now, but last time I used it, it didn't support Husk directly, so I just used my own. So in the Deadline monitor, I can click Submit, Husk Standalone Submission, which will pop up this submission window where I can point it to all of the USD files I want to render. Set the renderer, frame range, and chunk size, as well as any extra command line options. I find it useful to leave the res scale option here, so I can easily spit out half or quarter res tests. The downside to this approach is that it won't pick the frame ranges from the files automatically, so you need to adjust it per shot. I'm hoping I'll get around to adding that one of these days, but I've been using this method for over a year now, and it hasn't been too bad to just set the frame ranges manually. If I click Submit, it'll start rendering all of the USD files through Husk. For XPU, it can also render each batch of frames on a separate GPU, which depending on your scene can give a pretty noticeable speed increase. And that's about everything. Thanks for watching. I hope someone out there finds this useful, because making this video was a much bigger endeavor than I anticipated. I really enjoy working with LOPs and USD, but there's definitely been a learning curve, so I've been wanting to get this out there for a while to help kickstart any less technically oriented artists who want to give it a try. There are a few tips and things I didn't get to cover, but this video is long enough as it is. Anyway, one last note to end on. Don't forget that the most important thing is making good looking frames. It doesn't matter if you use the most basic setup I covered, the most complicated one, or some other method you come up with. As long as you're pumping out good looking frames, you're doing it right.